And I appreciate everyone's patience with listening to me tell the same stories over and over again.
No, they're always slightly different.
That's right. I keep improving them.
Yeah.
As Mark Twain once said, never let the truth get in the way of a good story.
That's right.
Actually, so last time I saw her, she took me out to a little cafe there, very close to Stefan's Dome. And she said, "You know why I brought you here?" And I said, "No, Haiti, why did you bring me here?" She said, "Because this is the oldest cafe in Vienna, and this is where Beethoven and Mozart used to perform."
Wow.
That was 2 blocks or 3 blocks away from where you were, Andy.
Yep.
All right, gents. I'm going to start with some announcements. By the way, everybody, welcome. This is the East Bay Astronomical Society April 2023 general meeting. This is going to be our last meeting where we are entirely virtual. We are going to start next month with hybrid meetings. That means you are all invited to actually show up at the Chabot Space and Science Center at 7:30. Our time is going to be at 7:30, not 7. In the, correct me if I'm wrong, Dave, it's the Copernicus room, correct?
I think so.
Yeah, and that is where we'll hold the in-person section of the meeting. This is going to be a hybrid meeting. It means that there will also be a Zoom link. So those of you who feel like viewing from home will still be able to do so. So we have obtained all of the magical technology necessary to try and pull this off. Thank you, Alan Roche, who's not here tonight, but Alan was very helpful in helping me test all this stuff out in the last couple of weeks. And it looks like it actually all works. So we'll see how it goes. So once again, 7:30 on May, what's the date? May
20th.
May 20 in the Copernicus room or on Zoom.
And we're
hybrid
having
meeting.
Dinner with a speaker beforehand at
Yes.
5:30 at Hunan Yuan.
Yes, an actual dinner with the speaker.
With
not a virtual dinner without the speaker. We're going to have an actual dinner with the speaker at 5:30 with pot stickers. Yes, 5:30 Hunan Yuan, the usual place. We just haven't been there for a few years, but they are open.
Although they've moved slightly, so don't let that.
Oh, they're one door over now, right?
Yeah, on the other side of, anyway.
Red Boy. I'm not sure that may be rumor.
Oh, okay.
I don't notice that anything has changed. I was just by there the other day.
Well, I was not, so I defer to your expertise.
I could be suffering from a collective hallucination. It wouldn't be the first time.
No, we often do.
Yes. All right. Well, that's really all I got. Or just a reminder, we will take questions at the end. We'll field them through Zoom and through Facebook. So please feel free to use the chat and QA section on Zoom. And if you're on Facebook, feel free to enter any questions in the comments section, and Andy will get them from me. So I leave it to the two of you. I'm going to mute myself, which everybody will be glad about, and you'll see me pop in a little bit later. So you all have a good time.
They won't be as happy as when I mute myself. That's another thing to say. By the way, before I forget, I want to say that next month's speaker is Dr. Adrienne Kuhl, who is one of the world's great experts on globular clusters. She's from San Francisco State. And so you're going to learn everything you've ever wanted to know about globular clusters. And if I'm not careful, I'll start talking about that. But instead, I'm going to introduce tonight's speaker, who I'm extremely excited about having. So Andy Rivkin is the lead investigator on the DART mission, which was tremendously successful. I mean, I was stunned when I saw the video, and we were all like, when it first happened, Andy, we were all like screaming and yelling and hollering in excitement. So Andy received his PhD in planetary astronomy from the University of Arizona in 1997. Planetary astronomy, University of Arizona. We seem to have a lot of friends who've done that, Andy. I don't know what it is about. It's a great place.
It's cool. Yeah.
A very cool place. I have a lot of friends who went there. He's at Johns Hopkins University now at the Applied Physics Laboratory, And he's particularly interested in near-infrared spectroscopy and spectrophotometry of asteroids. And he's interested in those asteroids that have evidence of water or organic materials. I wonder why. And detectable in the infrared reflectance spectrum. And this pursuit has led him to various interesting discoveries. He has particular interest in the dwarf planet Ceres. By the way, Andy, wasn't the Dawn mission really cool? That's another story.
Yeah, it was amazing.
Yeah,
That was
just amazing. And interested in helping to, he has a particular interest in asteroids that pose a threat to Earth, should one be discovered. And to that effect, he is the lead investigator. Is that the correct term to use, Andy?
Yeah, I think that's right. Yep.
For the DART mission, which was a focused spacecraft designed to direct itself to impact an asteroid at 14,000 miles per hour, approximately 4 miles per second. And its target, which posed no threat to the Earth, was the asteroid Dimorphos, which is Greek for two forms, and orbits a larger asteroid called Didymos. Forgive my Greek pronunciation for those of you out in the audience. The spacecraft was launched from this state, from Vandenberg Air Force Base, on November 23rd, 2021, and successfully collided with Dimorphos on September 26th, 2022. Andy, I can talk about this, but it's much better if you talk about it. Without any further ado, Dr. Andy Rivkin. Go ahead, Andy.
All right, thank you so much for having me here. I'm gonna share my screen and then I'm gonna turn my camera off to save a little bandwidth. Okay, so as noted, I'm here to talk about the double asteroid redirection test, which was NASA's first planetary defense test mission. You know, often when giving talks or people find out what I do, they say, when is the next time we're going to get hit? And the answer they don't expect, but which is the real answer, is we are going to get hit today. We're probably going to get hit in the next hour or two, because anytime you see anything like a shooting star, you're witnessing an impact. It's an impact of something very tiny, but it is an impact of, you know, extraterrestrial material that is derived from an asteroid or a comet. Something like 100 to 300 tons of material hits the Earth every day. And if you go somewhere dark, which is maybe not exactly where you are, anywhere in the bay, but if you get out up into the mountains or out into the desert, you might see 5 to 10 impacts, shooting stars, meteors per hour in a dark site. So this material is going to be small, maybe millimeter sized or smaller, maybe a gram or two of mass. Most of it doesn't even reach the ground. Bigger things do hit the Earth. When I was in my early 20s, just starting grad school, there was an impact in the northeastern United States, pretty close to where I grew up. You can see a movie there on the right showing what it looked like from, I think, Pittsburgh. I'll play it again, but this was an asteroid that was maybe the size of the chair that I'm sitting in that you can't see, maybe the chair you're sitting in, size of the couch you're sitting on, a couple of meters in size. And it airburst over the eastern USA. It was a Friday night. A lot of people were at their kids' high school football games, so they had their bulky 1992 era video cameras and took pictures of it and video of it. The astronomers were then able to go back and work out where the orbit was, and sure enough, it was an asteroid. They picked up pieces. This young woman, who was, I guess, probably maybe a little younger than I was very unlucky, and her car got totaled. And that piece of rock that you can see there on the right, about a foot in size, is what hit the car, totaled the car. Her insurance didn't cover it, because whose insurance covers that sort of thing? But she did sell the car to gem and mineral dealers, who then took it on tour around the US. Once again, larger things than that hit the Earth. You have to be very unlucky to have an impact like that be a problem. About 10 years ago, in the Russian city of Chelyabinsk, which is in Siberia, there was a bigger impact. Dashboard cameras around the city again captured this impact, this big flash over the city. And then after the flash, maybe a minute or so later, the shock wave arrived. And when the shock wave arrived, there were consequences, you know, a lot of broken glass, a lot of broken windows, a lot of very startled people around the city of Chelyabinsk. trying to sort out what happened. This last shot here from a school where there was the flash, there was the bang, there was the shock. The kids didn't know what was going on. The teachers didn't know what was going on. So this was a very big surprise. This was pieces, landed on the ground. Again, this is about 10 years ago. I was already active in the field, and when we saw these pictures, like this picture on the left of the ice and the hole in the ice, that was a perfect circle. We couldn't believe it. We thought this was not necessarily staged, but that someone was playing a joke. But sure enough, when divers went down to the bottom of that lake, they found pieces of the meteorite that hit Chelyabinsk. The object was about 20 to 25 meters in size. So 50, 60 feet across. And this map here shows the ground track of the Chelyabinsk impact. The different colors show the different ground effects where meteorites were recovered, where there was reported damage. And in all, something like 1,000 people were injured from broken glass. So this is not no real laughing matter. And you can imagine if something like this happened without warning over San Jose, over Oakland, over San Francisco, it could be we might not be so lucky as they were in Chelyabinsk, where no one died. These things happen all the time. This is a map of the Earth, of course, and the different colors and different sizes of circles show impacts that have been seen by U.S. government satellites looking downward, as they say. And while Chelyabinsk was the largest one that has been recorded since 1988, there are some others that aren't that much smaller. And as you can see, they've been recorded basically all over the world. There are no safe places from asteroid impacts, unlike some parts of the world get earthquakes, as you know, some parts of the world get tornadoes, some parts of the world get hurricanes. Every part of the world can potentially get an impact. So we've been looking for asteroids for some time. The searches really started in earnest in the 90s, and got a little extra push from the Chelyabinsk impact about 10 years ago, some extra urgency that some people felt. So on the largest size, the size that caused the mass extinctions, the extinction of the dinosaurs and the like, those are caused by objects that are about 10 kilometers in size. We think, in fact, we have very, very good reason to think we found all of the objects that are that size that are even vaguely close to Earth. We think there's 4 of them. We think we found them. On average, they impact the Earth every 100 to 200 million years. The last one was 66 million years ago. Again, we know that there's nothing close. We think we're good. One size down, one kilometer size. That's still a big enough size that we think it would cause global devastation. We think that it could cause, immediate climate change. It could lead to the collapse of civilization as agriculture and various supply chains, kind of fail. So the good news there, we think we've found most of these objects. We think there's about 900. We think we've found basically all of them. And once again, we think that we're in fine shape there. So those are not really the ones that we're worried about in a statistical sense or in a specific sense. If you go all the way down to the smallest size, the 4-meter size, so this is bigger than the couch. Maybe it's a few couches stacked up like you're in a frat house or something. Those objects that size hit the Earth once a year or so. They don't cause any damage unless you're very unlucky and your car happens to be just sitting underneath it. But for the most part, if there's a flash, maybe there's going to be meteorites, but no ill effects caused to the Earth, which is good because there's 500 million of those out there, and we've discovered only a tiny fraction. So now it's those kind of middle two columns, the 25-meter column and the 160-meter column, that are getting a lot more attention from scientists and policymakers. The 25-meter size, that's about the size of Chelyabinsk. We think those happen every few decades to 100 years. It would cause some kind of explosion like in Chelyabinsk. It could cause widespread injuries if people don't know they're coming. There's about 5 million of those. We've again discovered less than 1%. So we'd like to know where those are. And then the next size up, we've got about 160 meters here. Maybe it's 140 to 160 meters. Those cause definite ground damage when they hit. They could give you a crater that's a mile in diameter, half a mile in diameter. Again, if they were to hit a metro area, it would absolutely be the worst natural disaster in human history if we didn't see that coming. If we did see it coming, then maybe we could do something about it. We certainly could try to evacuate an area, but there are a couple, 20,000 of these kinds of objects we think that are out there. We found fewer than half. And while they hit every 25,000 years on average, the fact that we don't know where most of them are means that, in principle, we can't count on that average helping us. Anyone who's played roulette knows that on average your number is going to come up once every 40 spins, but that doesn't mean that it can't come up next, or you can't be waiting a long time. So people are searching the skies. We have the searches going. We don't know of any asteroids that are incoming, but that's why we want to do these searches. And it's also why we'll want to be prepared in case something is found. So planetary defense is basically the field whose job it is to look for these objects, to see if they are there, to determine if their orbits are going to intersect the Earth and they're going to be a problem, and also to come up with strategies and contingencies for what to do if an object is found to be en route. So this graphic here on the right shows a couple of different planetary defense strategies that have been identified and are being matured. The best one for the job depends on the amount of warning time we have, which goes back to the search, and the size of the object. So the different colors here show kind of different overall approaches. Something like the Chelyabinsk impactor, 25 meters in size, as long as we had some warning time, we would just tell people, hey, there's going to be something small that's going to come in near your city. There's going to be a flash. Stay away from the windows. Open the windows maybe so the shockwave doesn't break them. And, we'll replace your window. It's going to be much cheaper to go and replace every window in town than it is to launch some mission to do something about this. The red up there at the top, nuclear deflection, nuclear disruption, the biggest, most capable tool that we have as a species is a nuclear package, as some prefer to call it. So that's the most bang for the buck. But we want to develop things so that those are not our only two choices, is civil defense or a nuke. So kinetic impactors are part of that developing a new tool. And what a kinetic impactor is a very simple concept. You've got the animation there on the right, which hopefully you're seeing. Basically, you ram your spacecraft into the asteroid you're worried about, and that change in the asteroid's momentum from the spacecraft changes the orbit of the asteroid so that the asteroid is not at the same place at the same time as the Earth. And then everyone's happy. There are still, at least at the time the slide was made, a little before the impact, there were still some unknowns that we wanted to figure out. The momentum of the spacecraft was known, for instance, but the asteroid being hit by the impactor is not a closed system. There's debris that we imagined and has been created by the impact. That debris is carrying its own momentum. We didn't know how much debris was going to be made. We didn't know how much momentum it was going to carry, and that's going to change the overall story. So ideally, we wanted to have a test flight. The trick is that on this graphic here to the right, both the Earth and the asteroid are moving around the sun at something like 30 kilometers a second or 20 miles a second. We want to change the speed of the asteroid by a few inches per second or less, because in general, we want to keep the asteroid in one piece if we can, and just move the one piece. So we just have one thing to keep track of. So measuring a speed change of a few inches or an inch per second compared to 20 miles a second is hard. You either need a second spacecraft, which then increases complexity and increases cost. And for a test, people were not super keen on that, or we had to come up with some other clever idea. So Dr. Andy Cheng, who works at the Applied Physics Laboratory with me, came up with that clever idea. And that's based on the fact that some asteroids have moons. Here on the right, this is an animation showing radar data for a double asteroid system. The large body is, I believe, called Moshup. The small one's called Squanet. These used to have a different provisional name. So I think the new name only came in relatively recently, so you'll pardon me. So while asteroids, including this system here on the right, go around the sun at 20 miles a second, the moon is going around the main body at more like 4 inches a second, 5 inches a second. So if you want to change the speed of something from 4 inches a second to 4.5 inches a second, that's easy to measure. Also, and this is an astronomy club, astronomy society, we also could use light curves, which I'll talk about a little later, and the fact that for many of these binary systems, they're eclipsing binaries, so we could do the measurements we needed from telescopes from the Earth. So we don't need a second spacecraft at all. So that made this a low-cost, easy way to do the experiment we wanted to do. So this is, kind of the one slide summary of the DART mission. Everything, all the name, everything in the name means something. The double asteroid redirection test, double asteroid, we're going to a binary system. Redirection, we're changing the orbit of one of the bodies of the moon, and it's a test. This is an experiment. This was not a dangerous asteroid. We did not make it a dangerous asteroid. We are testing out this capability. So the DART mission was launched from Vandenberg Space Force Base. It's now Space Force Base in November 2021. As noted, we impacted a little over 7 months ago. In last September, we hit the object Dimorphos, which is a 150-meter object. It's orbiting the asteroid Didymos, which is a 760-meter object. It carried a CubeSat made by the Italian Space Agency, and then we did these observations from the Earth after LeechCube passed on by. Here's the scale of some of these objects. So DART itself, not counting the solar panels, is about the size of a vending machine. If you include the solar panels, kind of tip to tip, it's more like the size of a bus. Dimorphos, the object that was the target, is about the size of one of the pyramids of Egypt, for those of you that have done that. Didymos, and this gets into a little bit of a funny point for me. The long axis of Didymos is similar to the height of our tallest skyscrapers. Obviously, the asteroids have much more volume because they're, big round things instead of skinny skyscrapers. But at least in these other senses, this is a very human-sized, human-scaled system. And, it doesn't, you can imagine what the pyramids of Giza look like. That's about the size of, again, the target asteroid. Here's just a quick look at this depiction of the spacecraft and the different technologies that were carried. The most important ones for our talk today are LiCiCube, which again is the Italian CubeSat, SmartNav, which is the autonomous navigation system developed at APL, Draco, which is the camera and is the only instrument on board DART, and Draco is a descendant, I guess a cousin perhaps, of the LORI camera, which is on New Horizons out past Pluto. And it's also a cousin of the Lucy LORI camera, which is on the Lucy spacecraft heading out to the Jupiter Trojan asteroids. I'll also note the rollout solar arrays, which are pretty cool. Here's a quick look at LiCiCube. This CubeSat is about the size of a cereal box. It was provided by the Italian Space Agency. It has two cameras. One was a higher resolution monochrome camera called Leia. And then there is a color imager on board, which had lower spatial resolution called Luke. So obviously Star Wars fans in Italy. It was deployed about 2 weeks prior to the DART impact. It backed off and made sure it also didn't hit, and then made its closest approach a few minutes after DART did, so it could record the impact. There are 4 things that DART needed to do for NASA to be satisfied, and that's what we all want. All of us that are involved with missions want NASA to be happy with what we did. So these 4 things are listed here. We needed to impact Dimorphos last fall. We needed to change the orbit period of Dimorphos. It started at 11 hours and 55 minutes. We needed to change that by at least 73 seconds. The 73 seconds comes from what we thought was going to be observable after a month had elapsed. The minimum observable after a month had elapsed. So that's where the 73 seconds come from. It wasn't what we thought we would do. It was kind of the minimum we thought we could detect. We needed to measure the period change to a particular precision. And then we needed to measure this factor called beta, which is the momentum enhancement factor. It's how much the momentum of Dimorphos changed compared to the amount of momentum brought in by DART. And that figure there is a very psychedelic looking cutaway view of an impact simulation. So for those of you that don't know what spacecraft look like, just a few slides here showing the process. This is from May 2020. Of course, this is only a few months after the pandemic started. And so a lot of our usual practices had to be changed. Usually there'd be a lot of people in this room. Instead, everyone was undergoing social distancing. They cut the number of people in the room by a large factor, used a lot more virtual tests, virtual meetings. People would hold up their iPhones in places so that people online could see. And at this point, the spacecraft, like I said, it was about the size of a vending machine. Doesn't necessarily look that different from the interior of a vending machine at this point. It's just kind of some wires and some cables and cards. Here's the rollout solar array. You can see this roll here. This is when it's launched. It was all rolled up, as you'll see, and then it kind of rolled out in flight. Here's a couple of very happy-looking Italian engineers after they have attached LiCiCube to the side of the spacecraft. Here's the solar arrays all rolled up. Here's kind of the last inspection before sending it off. Here's some foil put on to help control the thermal, the temperature of the spacecraft. And then it was literally put on a truck in Maryland and driven across the country. There were 2 drivers. They only really stopped the truck to switch drivers and let the other driver go to sleep. So that went well. They went across the country in just a couple of days. And so, yes, this left the Applied Physics Lab, APL, where I work. Here it is, getting ready to go on the lab, on the pad. You can see an engineer standing here looking at this small spacecraft and what was a fairing that really could have held a lot more stuff, but that was all we needed it for. Put on top of this used SpaceX rocket. I think this was the first deep space science mission that SpaceX flew. And I think it was also the first NASA mission flown on a used rocket. And then the launch was beautiful. We were not sure what to expect. Other launches kind of were in foggy conditions, and viewers didn't get to see too much. But they were a different time of year. We had a great view, great conditions. So nothing but praise there. And I'll also show, this is a bit of a personal thing. So it was really an amazing process to be able to watch this. This is the first mission I've been involved with. This is my friend and colleague, Nancy Chabot. No relation to the Chabot Science Center, as I understand it. But here we are getting to see the spacecraft up close. Here we are on the pad. There it is behind us. And of course, there was the launch. There was video coverage. So we got to see it getting, the upper stages, letting go of it, and it heading off into space. And here is DART and the booster is tumbling, following behind, as observed by a telescope that night as it was leaving. So this shows the trajectory taken. This is looking from above the North Pole of the solar system and kind of at an angle. So DART was launched. Its orbit was very similar to the Earth's. So it didn't go very far. If you're a basketball fan, there's a question about whether this would have been a block or a charge, because DART kind of got into position and arguably was set while Dimorphos came screaming in. So the encounter took place while Didymos was very close to the Earth, which allowed a lot of our telescopes and radar to be used. Which it wouldn't have been had the impact been at other points at other times. This shows kind of a few images at key moments in those last few hours. If you can't see here, this little pixel here at the middle, that is what the Didymos system, Didymos plus Dimorphos, looked like at 4 hours out, when the SmartNav autonomous navigation was started up. So at this point, 4 hours out, 90,000 kilometers out, so that's something like 50 to 60,000 miles out, DART was allowed to steer its way in. A little over an hour out, and again, you can't really see too much, but if you blow it up, Dimorphos is separated. It's about 2 pixels across, and that's when DART thought or was detecting Dimorphos for the first time, and the engineers said, "Yes, you've found it. Go ahead and now lock onto Dimorphos instead of Didymos." At 2.5 minutes out or so, SmartNav was told to stop steering and to just coast. The engineers had estimated that at that point, any additional commands that were given, any additional steering, would perhaps be as likely to take it off course as to keep it on course. This is also the best view of all of Didymos that we got. Didymos, if you remember, if you watched, Didymos kind of made its way out the corner. And then here we have the last full image taken 2 seconds before the impact, 12 kilometers out, something like 6 or 7 miles out, and 30 meters across. So these rocks could fit probably in the room you're sitting in. Here's the sped up version of the last 5.5 minutes. The last 6 images are done real time. We love this movie. We show this movie all the time in our talks. You'll see another version of it shortly. We got to watch this from the Applied Physics Lab. We had an event out on the lawn. Some of us were on NASA TV earlier in the night, as I was, and then I got to enjoy the watching this with the rest of the crew who had worked so hard to bring us to this moment. So it was a really thrilling time, both in a science thrill and an emotional thrill. Again, here's just kind of our last view. This is a blow up of the last good view of Didymos, kind of rotated a bit. And of course, as asteroid scientists, we wished we had seen more of Didymos. We will, as I'll talk about a little bit, we will see more of Didymos in a few years, but we got these tantalizing views. But DART had work to do, and the work it had to do was to hit this guy, not study this guy. So this is a view of Dimorphos. It's not the closest view, but it's a good one I'm going to show here, because one of the things we needed to do was get the shape of Dimorphos really well. And so you can see this part is lit, and then you've got this thing here kind of off at the tail, and this is a rock that's sticking up high enough to still see the sun, but this area here is low. We can't really necessarily tell from this view where the edge of Dimorphos is. You might think, okay, this is probably the edge. But we purposefully picked a time of arrival such that we would get reflected light from Didymos onto Dimorphos. Didymos was off here to the right. So just like we get Earth shine at some phases of the moon, we got Didymos shine. So we can stretch this image here. And when you do that, you can actually see a lot more detail. You can see that here's some rocks sticking off the edge. You can see the limb of Dimorphos comes way out here. Maybe here's another rock sticking up. And so if we kind of clear out the glare, we think this is pretty much the shape of Dimorphos. So folks were working on that. We have some papers that have come out, and a shape model, an actual shape model that's been developed from images like this and others. We have a theme for naming objects and naming features, naming rocks on Dimorphos and Didymos. That's percussion musical instruments. So these are the names that have been approved so far. And these three here, the A, B, and C, Atabaki, Bowran, and Kakavela, are basically at the impact site. This again shows this close up, and we think we hit pretty close to the middle here. We hit within 25 meters of the center of figure, so very close to where we were aiming, and kind of touched. People on the team have been interested in what touched first. We think that probably this solar array touched Atabaki rock first, and then whether this solar array hit or grazed Bowran is not clear, but then the main body of the spacecraft mostly hit in between. LichaCube was following in. LichaCube was taking images, and you can see that it gets bright right at the point, when we hit. So again, this is about counting down the time to impact. This kind of donut, it wasn't great focus, unfortunately, but we could still see that, again, it got bright on Dimorphos as the debris was thrown up into space and lit up by the sun. The Luke camera got better views. This is approaching the system, and you see that mess there. That's the ejectocone. And then we start to retreat from the system. You can see this dark halo here, which is where the debris is so thick that the sun can't get through it. So we'll show it again. And again, we are approaching the system. You're coming down kind of the throat of a cone. And this debris cloud coming out from Dimorphos as you pass Didymos, the larger body, and again, we're now retreating from the system, looking backward and seeing that cone from the back. This image is aesthetically pleasing. We like this one a lot. This also shows kind of how far that debris and these rays from the debris stretch. Each larger square has the contrast stretched by a factor of 2 compared to the next smaller square. And you can see these filaments of rock and dust and gravel coming out from Dimorphos. This larger blob here on the bottom right is Didymos. And this is like when you see a raid crater on the moon, except Didymos doesn't have, and Dimorphos doesn't have enough gravity to bring this debris back onto the surface. So instead, these rays are just escaping into space, which then brings us to the next part of this, which is, within a few minutes, LiCiCube had gone on its way, and the job fell to these telescopes on Earth to follow up, and in space, actually. So we had telescopes on all 7 continents that have been participating in the observing campaign and contributing. As I said, 3 in space, the Hubble Space Telescope, JWST, and the Lucy spacecraft, which, as I said earlier, is on its way to the Trojan asteroids of Jupiter, happened to be in the vicinity at the time. It was close to having an Earth encounter, and so they turned their cameras at Didymos as well. The impact was highest in the sky just about at Reunion. Australia, Eastern Australia would have been able to see it, but it was daytime. So the observations at the impact time were done from kind of this Indian Ocean area, Kenya, South Africa, Israel. We know there are observations from Uzbekistan, Georgia. There were observations from Kazakhstan from people who are not on the team, but got some great data. And as I said, I was watching the impact out on the lawn outside the Applied Physics Lab. We watched the impact on a big screen. There was that partial red image. It was amazing. I got up to refill my beer, and the APL Slack started, the dark Slack started to buzz, and people were saying, we see it getting brighter in Kenya. We see it getting brighter in South Africa. And then we started getting movies like this. So this was on the right here, what was seen from the 1 meter telescope in South Africa. This sudden brightening, and then this puff of a material, this vapor plume coming off of the system. As I said, there's a paper with some data from Kazakhstan where they observed it, and again got some amazing data. Our team has got our own data like this that we are also planning to writing up and planning to publish soon. But this was just this amazing, unexpected moment here. As I said, we had telescopes from all over the world to prove it. Here are different images from each continent. Again, this is an astronomy club, so I'm sure you recognize the different approaches here, whether you're gonna track with the asteroid and get the stars trailing, whether you're just going to take short exposures, or what, whether you're going to flip, have the image flipped or not. We had Hubble and JWST time within a few hours of the impact. This cross here is the diffraction pattern in Hubble. This 6-pointed star is the diffraction pattern for JWST, but everything else is debris coming out of the system. These squiggles here, this clump here, that's all debris that we are working on connecting back to the LiCiCube images to say, did this ray that we saw, come off of Dimorphos 10 minutes after the impact, can we connect that to, this ray, say, or that ray a few hours later? Here's a movie showing how the tail evolved and how the ejecta evolved from about an hour before the impact, where there was nothing, to almost 3 weeks after the impact. And I'll run through it again. Then the frames are timed to be with the relevant time here. So you get this ejecta cone kind of coming off at 12 o'clock and at 8 o'clock. And then that evolves into this tail, and there's this double tail, and these linear striae, as comet astronomers call them, coming off. So we'll do this one more time. Just this amazing view, these features that we're still figuring out, and will, are telling us about the surface properties of Dimorphos. And then these images, this movie was taken from a Earth-based telescope in New Zealand, again covering kind of the first month. Each frame is an average of all of that night's data, and you can see this again ejectocone coming off at 1 and 8 o'clock, kind of slowly disappearing, and this tail forming and swinging around clockwise. So just this amazing data. This is the pretty pictures part of the talk. Once again, ground-based data from the Very Large Telescope in Chile. This is all showing us the same thing, but at different wavelengths and at different times, and letting us piece together the particle size distribution of what's in the tail, how much sand versus gravel versus fist size cobbles is there, and where they were, which part of the impact site they were derived from. The tail persisted. Here's a movie from the Lowell Discovery Telescope, several weeks, almost 2 months after the impact. Here's an image Christmas Eve, the good folks of the Magdalena Ridge Observatory, Eileen and Bill Ryan, observing on Christmas Day, 3 months later. Here's a movie from February from, again, the Lowell Discovery Telescope, where the tail has gotten fainter, but it's still there, in February, still there in March. So it's hung on a long time. And this is, I find this is kind of crazy. So Dimorphos is only about as big as the vehicle assembly building there. I said the Great Pyramid of Egypt. It's also about as big as this building. It's a big building, but it's a human-sized building. You can see cars there. It's big, but it's not incomprehensibly big. The debris tail, so the length of that tail is tens of thousands of kilometers. And at the time I made this slide, it stretched most of the way around the Earth. It now stretches all the way around the Earth in length. Obviously, it's not here at the Earth. And then the amount of material involved is, we think it's something like 50 to 60 railroad cars worth of material, worth of sand and gravel and the like. So again, that's a lot of railroad cars, but it's not like, we haven't seen, probably not like you haven't seen railroad trains that are tens and hundreds of cars long. So it's not crazy incomprehensibly long. So it just blows my mind that something this size with this much material can give you a tail that stretches this long, that looks like this months and months and months, 6 months after the impact. So all that's great. It's not what NASA wanted us to do. It's not one of our big 4 things. It'll help us, but it's not one of those things. So we used light curves to make the measurements we actually needed to make. This shows how the Didymos system looked in the days after the impact, Dimorphos going around Didymos there and moving into Didymos's shadow and casting a shadow on Dimorphos. From the Earth and from the space telescopes, they only ever appeared as a single point of light, as you saw. So we measured the brightness of that point of light going up and down as the shadows are cast, and that gives us that bottom trace. By measuring how often we get those dips, we can measure the length of Dimorphos's period. Before the impact, we've been doing that for years. That's where we said, okay, there's an 11-hour and 55-minute period. We began doing it as soon as we could after the impact to measure the new period, which would then give us the information we need. And so here's some data. The top shows the data we had at the time we made this slide, which is early October, with 2 callouts here. So here on the bottom left, this is the data from September 29th. If there was an 11-hour, 55-minute orbit period and we hadn't done anything, we would have gotten a dip here. Instead, we got a dip here. On October 4th, if we hadn't done anything, we would have gotten a dip here. Instead, we got a dip here. These two dips along all the dips of the same color up on the top one gave us showed that we had an 11-hour, 23-minute period. I think now it's 11 hours and 22 minutes with the new calculations. But basically an 11-hour and 23-minute period. We also got radar data. For those of you that are not familiar with radar data, these are radar images. Up and down, this is the range. So the further things are, the further down the image from the further things are from the antenna, the farther down the image they are. So these are a little further away than that. And then the left and right is Doppler frequency. So things that are moving toward you are on the right. Things that are moving away from you are on the left. So this is what Didymos looks like. This is rotating toward you. This is rotating away from you. And they're all pretty close to the same distance. Dimorphos is here. People that study radar are very happy with this data, even if it's maybe for folks that don't study radar, or maybe it's less obvious, but the people who study radar are all unanimously convinced, yes, that's Dimorphos. So once again, you can determine where it should have been and where it is, fit a new orbit, and it agrees with an 11-hour and 23-minute period. So this is an individual, separate information about that. So for this momentum transfer efficiency, how did we do? On the left there would be, we would not move Dimorphos very much if there was no ejecta. And then if we make some ejecta, it moves faster. We make lots of ejecta, it moves much faster. So using that very scientific, scale there, we moved it somewhere between, we gave it somewhere between some and lots of ejecta. This momentum enhancement factor is about 3.6. We changed the period by, again, 33 minutes. If we had made no ejecta, if we just buried DART, we think we would have made a change of about 7 minutes. So this was within our range of what we thought was possible. It was not necessarily what we thought was most likely. We certainly had to plan for this case here on the left. So I don't think we were surprised in the sense of we never thought that could happen. I think to the extent we were surprised, it's because we thought the most boring thing was going to happen, which was this over here on the left. So the folks working on the impact simulations have been hard at work. This is a pre-impact movie showing some simulations of how the DART doing a belly flop into a model sphere. We have better models now that are more informed. So here on the left, you've got that movie I showed before of LiCiCube coming in. Here on the right is a impact working group simulation where they are trying to match everything. They're trying to match the delta V that we gave to Dimorphos. They're trying to match the kind of the way the ejecta curtain looks. They're putting rocks on the surface that are correct. And so this is kind of where we are at. And again, this has been presented at some conferences and we're working on getting the papers out. And some papers have already gotten out. Just last week, the first 4 papers from the DART mission have been released in Nature. They are all available open access, so you should be able to read them if you want. These top 4 are from the team and talk about the various aspects of the impact that we've got. We intercepted what the shape of the object is like, what the density we've adopted is. The data went into calculating the period change, the Hubble Space Telescope images and analysis, and then this beta factor. And then there's also a 5th paper done by the citizen science group led by the paper was led by Ariel Grakowski, who's I think local to you folks. So we can go back to this. We can check off number 1, number 2, number 4. Yes, we hit. Yes, we changed the period by at least 73 seconds. Yes, we measured beta. The third one, we're very close to getting. We've measured it to the right precision. We just need to publish it before we give ourselves the check. So we're in excellent shape here. NASA is happy with us. We have an international team who've done great work. We have people from dozens of countries, from dozens of institutions. We have hundreds of people who are on the investigation team who have just done this amazing job. And that's fitting because DART is a international mission, and planetary defense is an international issue. Here on the left, it shows, DART carried the Italian CubeSat. On the right, the Hera mission, which is going to be a follow-up, is going to be launching next year, and it will go back to the Didymos system. It will make measurements that DART could not make, like a measurement of the mass of Dimorphos instead of the estimate we made. It's going to carry its own CubeSats. It's going to carry a Japanese instrument. So we're very much looking forward to the Hera mission being a great bookend and a great complement to DART. DART ends at the end of September, so we only have a few months left, but we are still active in the places where you might expect to find missions. We have our website. We still have our Planetary Defender test that you can take and download your certificate. We are active on social media wherever NASA is. We also have our outreach page. Here's Nancy again, where you can find the instructions for printing 3D models of the spacecraft and the Didymos system, a toy bricks model of the spacecraft, and this AR experience where you can put the spacecraft into your pictures. You cannot put Nancy into those pictures, at least not via that AR experience. So no luck there for you. So in conclusion, DART was a great success. It demonstrated that kinetic impactor technology is a viable technique to potentially defend the Earth. This is not an operational capability, but it does show that this is doable, and it gives us data to calibrate our models at a scale that we've never had before. The large orbit period change shows that the ejecta contributed a significant amount of momentum, more momentum than what DART carried. And so in principle, if this is found to be true in general, this means that a kinetic impactor could be used on a larger object or at a later time than previously thought. And then from a big picture point of view, this was the first time that humanity moved a celestial object on purpose. And so that itself is also a kind of an interesting milestone, I'll put it that way. And with that, thank you for your time and attention, and I'm happy to take any questions you might have.
All right, thank you so much. Dave, you still out there?
I still am, yes. That
All
was
right.
absolutely wonderful, and I've got a million questions.
Andy, you could stop sharing the PowerPoint, and that way people could see our
You got it.
faces. Dave, we'll start with you. I'm sure you're always a good person to start with on questions because you always have them.
That's Andy. I have to tell you that the reason they made me program director was I asked more than 50% of the questions in any given meeting. My apologies. This first, Andy, I want to thank you very much. That was an absolutely wonderful and fascinating talk. But it also leads on to, like, I'm glad you mentioned Hera because I was going to ask you what's next. One of my big concerns are comets, because you went over the distribution for asteroids, but comets are unpredictable. It will have less lead time. They could be coming out at us from weird directions. One time in an interview I did, I described comets as the drunk drivers of the solar system because they don't follow a purely Newtonian trajectory. So is there a thought given to the idea of trying to deflect a comet?
Yeah, so there have been the studies that have been done via the national academies and other folks. They've tended to look at the problem in an actuarial sense, right? In a statistical sense. And so the reason that so 20 years ago, whenever it was, 30 years ago, Congress tasked NASA with finding all of the 1 kilometer objects. And that was because 1 kilometer was the size that would, destroy civilization. The next one, the next task was find all of the objects 140 meters in size, larger, and 140 meters in size was picked because when they looked at the risk in this actuarial sense, they said, if we can find everything down to 140 meters, then 90% of the remaining risk goes away.
Yeah.
Once they do that, it's a bit more of an open question once we achieve that goal, because comets are that then you start to get down to the point where comets start to be one of the biggest remaining risks. Comets are really, really hard to find, especially when they're, far away. And for asteroids, right, you can say, here's this asteroid orbit. We know it well. We can get 30 years of warning, so you can do something. Addressing a comet, finding a comet that you know is going to be a problem 30 years ahead is a very, very challenging question. Yes. And there's kind of a policy question of, if you say there's a 1% chance, if there's a 1% chance we're going to do something, but then 99 times out of 100, you've wasted your $500 million, and people also are going to get tired of that. So I think people will get to the point of maybe trying to develop some late stage, instead of the asteroid thing where you find them early and you do something, maybe you say, okay, look, comets are made out of ice, and maybe, if you think they're going to hit, you just need to bust them up. And unlike asteroids, I said you want to keep them together. Maybe comets, you want to bust them up and let the ice just drive all the pieces far off. But I think we're still stuck at the point where trying to figure out how to find dangerous comets is still a bit of a question.
Okay, and that leads, forgive me, Rich, for jumping in, but that also leads to my other question here, which is, I know this is a violation of the, what is it, the International Convention of using nuclear weapons in space. But one would think that if there's ever was a good use for nuclear weapons, this would be it, because as I've argued among people in the community, the first time you try to do something, it never works, except actually you've violated that rule here. But I could just see, if a comet was coming in at us, even if we had a couple of years warning, with a nuke, we would not have practice. This is something I've been arguing we have to practice doing. And again, there's also this question about what is the cohesiveness of a comet, of cometary material? How would it respond to a thermonuclear device exploding right next to it? So, I've been a big fan advocating that that we've got to test these things beforehand. So is there any thought of discussion of this that you've heard in the community?
Yeah, there is.
Especially from people like Lawrence Livermore, I would anticipate.
Yeah, there is discussion. It is a very divisive topic.
Yeah, I know.
Part of the reason that we worked on developing a kinetic impactor, like I said, was so that we had at least some other possibility.
Yeah.
The meeting, the Planetary Defense Conference was just held in Vienna at the United Nations, and it brings together every 2 years. It's a I don't know if I would say it's a fun meeting. It's a very informative meeting, and it brings together scientists, it brings together engineers, it brings together policy people, it brings together lawyers. And the discussion seemed to be, the legal situation seems to be that, yes, it would be against international law. That the Security Council could decide that it's okay, but the Security Council is not, that it would be unprecedented for the Security Council to say it's okay, but it's not an emergency, to give a waiver, to either say we're going to give you a blanket okay in case this is ever a problem, or to say, yeah, go ahead and test it. There is an argument that if you don't get the okay, you could just deal with the consequences. But I think the odds are minuscule that certainly that the United States or any of our allies would do that. And I think the consequences of anyone doing it would be pretty dire if they didn't have everyone on board.
Well, this dovetails with a question that Jeff asked. That's kind of one of those, is this a yes or a no type of questions. Can you quickly say, seriously, can we now deflect an object that can cause a nuclear winter? I get that it's a matter of time, years versus weeks, but are we even close?
So it comes down to warning time ultimately. So if we found something dimorphos size, which is not the size you're concerned about, but if we found something dimorphos sized that was going to hit us in a year, no, we would have to go to and there are exercises like this. It would become an evacuation, civil defense. I was involved in an exercise last year where the city of Winston-Salem, North Carolina, volunteered. They wanted to do their emergency practice, and said, okay, let's set it up so that we just have to evacuate North Carolina or that part of North Carolina.
Wow.
If we had 30 years to deflect something dimorphosized, yeah, I think we could do that. Absolutely. Something nuclear winter size, I'm not sure. Something that's the next problem is that every time you double something in size, you take the mass goes up by a factor of 8. So if you could deflect something with something dart sized, and you double the diameter, now you need 8 darts, or you need 8 times as long, 8 times as much warning time. Something a kilometer in size would almost certainly be big enough that we would want to use a nuke, but because otherwise you're sending hundreds and hundreds and hundreds of things like DART. But the odds are slim, so it's again kind of playing the odds. I know you asked if I could quickly say this. I guess I am not quickly saying it. It's all kind of there's a lot of case by case, and a lot of this is also policy, not science. So if a government was like, look, we are just not going to go the nuke route, then let's say next week we're going to get hit wet then. It depends. I mean, there are plans that people have looked at, again, with a last ditch. We find something next week. Can we take the nuclear arsenals we have now and do a near Earth, kiss all of our satellites goodbye, kiss all of our electronics goodbye, but maybe we have a chance of, people have looked at that. And it's honestly not clear. But again, a week versus a month versus a year versus it's the other problem, again, this is a statistical thing, is that it's the way that the probability of impact develops is it spends, often these things spend a long time at there's a 1% chance, there's a 1% chance, there's a 1% chance, there's a 3% chance, and in all of our experience, it gets to 2% and then it goes to 0. Something that is going to hit is going to be at 2%, it's going to be at 3%, it's going to be at 3%, and then it's going to go around the sun, it's going to be unobservable for a while, it's going to come back, and now, oh gosh, now it's at 20%, and then it's 20% chance it's going to hit in 50 years, and then it's going to be, well, now it's a 22% chance it's going to hit in 49 years, and at some point there's going to have to be the decision to do something about it, and the UN and countries have thresholds for that these countries have agreed on. So how are we so lucky over history? We dodged a bullet with Tunguska. The orbit wouldn't have had to have been that different, and the Russian capital would have been wiped out in 1908, and no one would have known what happened. It would have just been, holy crap, the St. Petersburg just got wiped out and we don't know what happened. Because it's 1908 and we have no idea. so, I think space is big and human history is short compared to the timescales we're talking about. And the odds are good that we are preparing for something, and God willing, we will never have to use it. Just like most of us, I think maybe all of us, have smoke detectors in our houses, and very, very few smoke detectors ever go off because there's a fire. They go off, it's the middle of the night and the batteries, whatever. But we all agree that having a smoke detector in our house is worth doing. So similarly, the program to search for asteroids, to make sure that we really are clear, to spend a bit of money to develop mitigation techniques in case we find something in the next 20 or 30 years. And then hopefully with the space telescopes that are being developed and the Rubin Observatory, hopefully in 30 years, 50 years, we can say, look, we are clear. We're clear. We know we're clear for the next 100 years or the next 200 years or whatever.
Except
so
for
now
comets.
we just need to monitor.
Except for
Except
comets.
for comets, yeah.
Right.
Yeah, sure.
But announcer
and comets are,
announcer
and
prevention.
comets are going to require a different, yeah, absolutely.
Interesting. All right, let's see. A lot of people thanking you for this talk on Facebook. No questions there, and no additional questions yet on Zoom. I mean, on the comet issue, I mean, is there any benefit to thinking about pre-positioning some type of device on the moon, or field of devices on the moon, so you don't have to build these heavy launch vehicles in short periods of time? I mean, people talk about it's a science fiction at this point, but I mean, is that like a topic of discussion at these conferences?
Yeah, absolutely. People talk about pre-positioning. People have done studies and are going to do more studies. The problem with pre-positioning is that comets can come from anywhere, and in a sense, asteroids can come from anywhere. So if you got your thing pre-positioned, but that's going to take care of some things, but you get to the point of like, we need to pre-position so many things that it's better to just build it from scratch.
It's the same problem. It's the same problem in the Pacific, and it's worse in the solar system.
Right, and in a sense, you could also imagine that in 1980. That NASA and the countries were like, all right, we're good. We're going to do this. We're going to pre-position things. We believe in this. They put the stuff out there, and we find something now that's going to hit us in 20 years. So we're going to say, great, let's use the 1980 technology.
All right.
Yeah. Or should we just do it? We think we can do it better now. I think ultimately the answer, and this is totally science fiction, if not video game, is that ultimately it's going to be, we're going to have point laser systems, set up, and it's going to be, we're not going to go out to them. We have whatever means of destroying the things when they're close, and it's not going to be a 10-kilometer comet. It's going to be a 200-meter comet or a 1-kilometer comet or whatever. But it's a tough question, and happily we like I said, we can't count on the odds remaining in our favor, but we can at least recognize that the odds are not against us. So
that's a good answer. Lori asked a question on Facebook. What about, and it's actually part of a larger question, which you didn't ask. What about satellites, a quarter of the way around the sun that can see what's happening, behind the sun? And I would think that, it comes down to putting an emphasis on detection and being able to, especially for comets, right? I mean, we get about a year's notice on a comet, right? Or not even most of the time. Sometimes we get a year's notice. But having instruments that could do surveys where they could be peering into parts of the solar system that don't correspond with our current orbit at the Earth's, on the current Earth orbit, would probably help us gain an advantage on comet detection.
Yeah, that's a great question and a great point. The NEO Surveyor mission, which NASA hopes to launch this decade, is going to be at one of, I forget if it's the Earth Sun L1 or Earth Sun L2, but there was a point at which people were considering sending a search telescope into the distance of Venus to orbit the sun at the distance of Venus, and because that way it could just look out. And right now at Earth, things need to look out and look in.
Yeah.
So if you go to Venus, you just have to look out. The problem or the challenge is that, okay, there are going to be, just like was suggested, there will be some times when the spacecraft is on the opposite side of the sun as the Earth, and it's hard to send data down from there. And so you have to, at least at the time people were talking about this 5 years ago or 10 years ago, the thought was, okay, so you need to have enough smarts on board the spacecraft to have it be able to take the data and be able to go, oh, hey, I think this thing may be a problem. And you have to either trust it to be right, or, hey, I found this thing, well, it looks like it's going to be close, but it's not going to be a problem. You either need to trust the onboard stuff to just have it give you the answer, hey, there's a thing, I don't think it's going to be a problem, or, hey, there's a thing, it is going to be a problem. Or you have to have it send down all the data
right
to Earth.
Right.
So there's again these engineering issues. It's also funny because something that certainly I thought at one point that's not obvious until you think about it. You go, well, why not just send something out to Neptune, right? And you've got your search thing out at Neptune, and then you're much closer. Except you're only closer to the things in that part of the solar system, and there's the again across the solar system. Now you're much further, and it's much worse. So
yep.
So yeah, there's a lot of non-intuitive things here.
I mean, Marianne asked the question. Hi, Marianne. How often have comets come very close to Earth? We don't really know the answer to that. I mean, the human observation of comets is pretty short in the overall history of the Earth. But I mean, how often is a close encounter with a comet to Earth? And I've never thought about that.
Well, it depends. Yeah, it depends on what you consider close. Comets, the comet that was visited by Rosetta, Churyumov-Gerasimenko, technically is a near-Earth object.
Yes.
The definition of a near-Earth object is something that has a perihelion less than 1.3 AU. That counts. Comet Halley technically is a near-Earth, same thing, near-Earth object.
I have a very good
Comet
example.
Encke, I think.
Comet Irasaraki-Alcock in that was very close. I mean, you could see the sucker moving.
Yeah, there's another way to answer the question too. How many distinct meteor showers do we have every year?
Oh.
And you can say those are comets that intersected Earth's orbit. So I would consider that to be a close encounter, even though it didn't hit the Earth. Right?
That's a great point. Arguably one of the first planetary defense, or one of the first impact panics, sort of clickbait sort of thing, was Comet Halley in 1910, because the Earth passed through the tail. And there was concern because they had just spectroscopically detected cyanide in comet tails. And so there was this concern that, oh my God, we're going to pass through the tail of Comet Halley and everyone's going to get poisoned.
They were selling gas masks.
Really?
Gas
for real?
Yeah.
I didn't know that.
Yeah. So we haven't had an impact. There are far fewer comets there are far fewer dangerous comets than dangerous asteroids, or potentially hazardous objects are mostly asteroids compared to comets. So thus far, again, there's been this good reason for focusing on asteroids. We are due a good comet, but we are not due a super close. We're not due a super duper close comet.
Yeah. All right.
I have a simple question.
Go for it.
Are there any thoughts to another impact mission?
So the I don't know if you're familiar with the decadal surveys here. So every 10 years, and this is various subfields in astronomy, the national academies NASA will commission a study, NASA plus NSF will commission a study of different subfields of astronomy where people get together, they prioritize what they want over the next 10 years. So for the first time, planetary defense was included in the Planetary Science Decadal Survey that came out last year. And so NASA will presumably follow those priorities. Another impact mission is included in you might want to do this, but there are other priorities. China is apparently planning to do one. In the short term, they're talking about launching in the next few years. There's not a lot of details about it, at least not a lot of details that have come out in public. They've talked about it at a few conferences in China that again have been reported. Their target is much smaller than Dimorphos, and it's a single object. So it will be a much more challenging intercept. I think they are planning to have a second spacecraft there that'll help them guide in. And to be honest, people on the DART team aren't sure they're not going to just destroy their object because it's much smaller. And we estimate that if Dimorphos had been half the size it is, that we might have destroyed it.
Wow.
We knew it wasn't. So that's okay, but again, a factor of 2 smaller means a factor of 8 less mass. And the Chinese are talking about visiting something, more like a factor of 5 times smaller than Dimorphos, so a factor of 100 less mass. So, maybe they have a tiny spacecraft. Maybe they're not going to come in as fast. Maybe they don't care if they destroy their object. But again, we don't have a whole lot of details on what they're thinking.
All right. All right, Andy. Well, thank you. Dave, thank you. Dave, safe travels to you because I know you're going away for a while.
Thank you.
And everyone, just a reminder that next month you'll have the opportunity to hear our speaker in person. It'll be Adrian Kuhl, and she'll be at Chabot at 7:30 p.m. So we're going back to our old schedule and live meetings with hybrid options. So if you prefer to watch the meeting from the comfort of home, you'll be able to do so. And I'll be sending out an email with a reminder about this and instructions for those who need it. Guess that's it. Best of luck to everyone.
I just
and
give a plug for the June talk. The June
talk please.
Will be Saturday, June 24th, and that'll be Dave Erskine. And Rich, you know far more about what he's going to speak about than I. So you can briefly describe that. I'd be much obliged.
Dave has been working on a mathematical solution for enhancing the resolution of spectroscopy and interferometry using a combined technology. It's called EDI, and he's talked about this to EAS in the past, but there have been some major advances in this technology and also some new purposes for it. And he'll be talking to the club about that. He's a local. He lives here in Oakland, and a really nice guy. And you found him in the woods, right?
Well, actually, my wife found him in the woods while she was out hiking at our local regional park, Lake Chabot.
Yeah, I usually see him for coffee. You found him in the woods, but he's a good speaker and he's a nice guy. So
Andy, it's a small universe, so be nice to everybody you meet. You can never tell who they might be, or maybe they're a potential source of funding. So be very nice.
Absolutely.
Andy, once again, thank you for an absolutely wonderful talk. I found it absolutely riveting.
Yeah, it was great.
I have a million more questions I could easily ask you. So thank you. Great talk.
All right.
Well, thanks for having me.
All right. Good night, everyone.
Good night, everyone.
Bye.